cool practical examples. And this is a little outside of what the book goes through. But I wanted to provide you with some actual like cool manifestations of this. So here I'm going to have my calculation and then the graph up here side by side. And so what I've done here is I've calculated the wave function for carbon monoxide and HCl using the harmonic oscillator model. Okay, so you can see the force constant for carbon monoxide is quite large, 1860 Newton per meter. And so that would be an example of a very stiff spring because we know carbon monoxide has got that triple bond, okay? Versus HCl, which has a very small force constant of 480 newtons per meter, and that's just because that's a single bond like so, okay? And so what that means, if you were to now use the reduced mass, so again, this M that I used here to calculate alpha, right, was from, you know, mass of hydrogen times mass of chlorine divided by mass of hydrogen plus mass of chlorine. And then same for over here, right? Mass of carbon times mass of oxygen over mass of carbon plus mass of oxygen for the mass. And we have to remember when we do reduced mass calculations, we're not doing it for the average periodic table mass. We have to specify which isotope, right? Because a DCl, a deuterium chloride, will have a very different reduced mass than an HCl. And so for those of you in the lab, this is a very cool experiment we can do. We can synthesize HCl or DCl in the Schlenk line and take spectra of it, and we can actually see the difference in the spectra when we replace the hydrogen with the deuterium. Excuse me. Okay, so using the force constant, using the reduced mass, I calculated alpha for carbon monoxide to be 4.8 picometers and alpha for HCl to be 10.9 picometers. And so as you can see right here, as a result, so HCl is in the orange, its wave function is much more spread out, okay? Because it's not as stiff of a spring. So when it vibrates, it can really elongate. So it physically elongates to a bigger distance, okay? And so you can see that, you know, 10.9 picometer, it's hard to say like, where's that 10.9 picometer showing up? But again, this alpha, right, because y is x divided by alpha, that really number is just setting the scale for our x-axis. And so here you can see this x-axis now, because I'm using realistic alphas, you know, that's in units of picometers, okay? And conversely, you can see the ground state of carbon monoxide is a much narrower, more compressed spring, which makes sense given that it's got a triple bond. So what's also cool, I calculated the wave functions for carbon monoxide and HCl for nu equals 1. And you can see similarly now, HCl really spreads out as it goes through this transition, okay? And so now in spectroscopy, what we observe in spectroscopy is the difference between these energy levels, all right? Remember, spectroscopy is the difference between these energy levels, which we know now, like if I draw this really quick here, we've got my ground state that looks like this. We've got my second excited state, which looks like this, okay? And we now know the difference between these two energies is given as h bar omega. So obviously each of these molecules will have different h bar omega spacings because they have different oscillator frequencies, they have different reduced masses, okay? And also what we can talk about the intensity of a spectroscopic transition.